Welcome to HotChips34. Session 4, Machine Learning.
Good morning, everyone, and welcome to the second day of Hot Chips. I'm Ronnie Krasinski from NVIDIA, and I'll be the chair of this exciting session, the first session on machine learning. So the first talk up today is from Groq on their software-defined scale-out tensor streaming multiprocessor. The speaker is Dennis Abts. Dennis is the chief architect at Groq, where he works on domain-specific parallel architectures for machine learning and HPC. Prior to Groq, Dennis spent 2 decades at Google and Cray, where he designed large-scale distributed systems. He holds 33 issued patents and co-authored over 24 technical papers spanning interconnection networks, memory system design, and reliability, distributed system coherence protocols, and synchronization. So let's go to the talk from Dennis.
Hi, and welcome to this presentation describing the Groq software-defined scale-out tensor streaming processor. Through this talk, I hope to motivate and describe our system from both a chip to a system architecture. This is work done with a number of collaborators at Groq. I want to acknowledge the team and thank them for their collaboration. It's a big team effort, and we're a startup, and it takes everybody to work hard and accomplish big goals. So thank you to the broader team. What I hope to do today is to give you a background on the TSP microarchitecture, to motivate how we build systems from that, to describe some workloads, and then leave you with a summary of what we just described. What we did is we started by taking a look at the software-defined approach that really re-examines where the software-hardware interfaces are in a multiprocessor. Specifically, we have a static dynamic interface where we have the compile time versus runtime. And we have a hardware-software interface that the ISA, or the instruction set architecture, is responsible for implementing and enforcing. And what we're describing here is an approach where we turn over more control to the software and use more of the silicon to do, well, hardware things, and leave the things that can be done in software where they are best served in the software stack. Designing for determinism requires that we make some design choices and really adhere to a design philosophy. We had to make sure that the hardware was completely controllable by the compiler. In other words, it wasn't about abstracting away the details of the hardware. It's about explicitly controlling the underlying hardware. And the compiler has an oracular view of what the hardware is doing at any given cycle. Unlike traditional systems, traditional CPUs, that embrace aggressive out-of-order execution, speculative execution, a lot of techniques to expose additional instruction-level parallelism and memory concurrency in the memory hierarchy. We've taken a different approach. We use just a single flat scratchpad memory that's 220 megabytes, and we allocate tensors in that memory explicitly so the compiler knows where the tensors are and how they're moving on chip. We describe the memory concurrency, and there's an abundance of memory concurrency that the compiler can take advantage of. We describe that through our partitioned global address space and make that accessible across the entire system. Complexity at the system level often creeps in because these systems grow to be tens of thousands of processing elements, often consisting of heterogeneous components like CPUs, GPUs, smart NICs, FPGAs, all of which have different failure characteristics and performance profiles. As a result, you end up with a lot of performance variation and response time latency variation, for example. And that latency variation ultimately slows down an internet scale application. Anything that requires a coordinated effort across the entire machine will ultimately be limited by the worst case latency across the network. So what we did is tried to avoid some of this waste, fraud, and abuse that crops up at the system level to introduce new techniques that help us load balance the system without the reactivity of adaptive routing and other aggressive techniques at the network level. So let's take a look at the microarchitecture. And we started with this concept of a homogeneous core, each of which contains certain computing elements: an integer, a unit, a floating point unit, a load store unit, and a network interface. And we disaggregated those functional units to make them SIMD functional units and lay them out next to each other so that we can control them and take advantage of their spatial locality. And so while this looks a little different than a conventional CPU, it allows us to execute in the same way that conventional CPU breaks down larger instructions into micro-ops. Similarly, we're breaking up deep learning operations into their constituent smaller micro-operations and executing those as an ensemble, which together accomplish a larger goal. And so if we just take a look at the chip architecture, we can see that the chip is organized in the spatial orientation where we have functional units laid out next to each other, and they collaborate with each other by passing operands and results between each other in an efficient way called chaining. We chain the output of one functional unit to the inputs of an adjacent downstream functional unit. On the chip, there's a large MXM module, which is our workhorse. It's our matrix unit, and it contains storage for 409,600 weights. In other words, a lot of weight parameters that we can take advantage of the data parallelism on the chip. What this allows us to do is to provide tremendous compute density with over 1 teraop per square millimeter of silicon area. So if we take a step back and look at the software abstractions this allows us, we have multiple different functional units on the chip. And those are organized into simple building blocks that are 320 elements long. This is the SIMD unit I was referring to. Each SIMD unit is controlled by an instruction dispatch unit, instruction control unit at the bottom of the chip. These functional units are laid out next to each other in the same way that you can think about abstractions or across different classes in software. So there's different specializations for these different functional units. We've got an MXM or a matrix unit, a vector unit for pointwise operations, an SXM or switch execution module for data reshaping, and a memory unit to handle on-chip memory. These are laid out next to each other and to take advantage of their spatial orientation. So we can stream data on the chip east and west and take advantage of that spatial locality. In a sense, capturing the data flow locality that's common in all these machine learning models. What this enables is an ISA that empowers our software stack. We explicitly turn over control to the software, specifically the compiler, so that it can reason about correctness and schedule instructions on the hardware from a first principle standpoint. Specifically, there's 144 on-chip instruction control units, each of which control the dispatch to their functional units that they're associated with. This allows us to keep the hardware overhead of dispatch very low. Less than 3% of the area is used for instruction decode and dispatch, while putting most of the chip's area to good use executing functional models. So one of the things is this provides a very simple abstraction to the compiler that each functional unit interacts with a set of stream register files. And these SRFs, as they're called, provide the conduit through which data inputs and data results are communicated to the other functional units. You can think about this as sort of a tensor assembly line that connects up the different functional units. And these stream registers are a very simple model for the compiler to reason about. It's only one cycle hop between each stream register. There's no arbiters, no queues, no reordering that's allowed either in load stores or network references. So the compiler truly does have oracular information that it can reason about the correctness of every program it generates. At the heart of this is an instruction set that is a domain-specific instruction set for operating on machine learning models. Specifically, We take machine learning operations like conv2D and we break them down into an ensemble of micro instructions that are executed across the chip at each different functional unit. They cooperate to produce this higher level instruction like a conv2D or a max pool operation. And the instructions are broken down in their different instruction set according to each functional unit. The data types supported by the hardware natively are both int, signed and unsigned int 8, as well as floating point 16, so half precision floating point. In addition, the vector unit, the vector processor that does pointwise elements, supports a superset of that, including FP32. So if we just take a look at the functional units, every functional unit has a certain number of compulsory instructions, namely instruction fetching, no-opping, and synchronization. And these are the fundamental instructions necessary to coordinate the execution. At the heart of the chip is our matrix multiply unit. The matrix engine operates by having a 320 element vector, and there's 320 features in each matrix, giving it a 320 by 320 integer operation. For floating point operations, we can do 320 by 160. This allows us to handle both integer and floating point. Floating point is a little unique since a pair of byte planes cooperate to produce one FP16 output. In the center of a chip is our vector execution module, or VXM. It's the vector pointwise operations that are common in machine learning models. For example, GALU or ReLU are common, as well as other transcendental functions are present in the vector unit to take advantage of pointwise operations. Each vector lane supports 16 ALUs, and that's connected up to our on-chip memory in SRAM through our memory functional unit. The memory functional unit has 88 slices across the chip, each of which can do one read and one write. So in principle, the memory system supports up to 176-way concurrent execution. That's a tremendous amount of memory concurrency to exploit. And then lastly, at the SXM is our switch execution module. And the SXM provides kind of the Swiss Army knife, data manipulation, data reshaping, on-chip data movements, and off-chip data movements. As we see here, this is referencing our chip-to-chip or C2C I/O, including PCIe is also handled by the SXM unit. So let's take a step back and see how we package this all together to create systems from these components. We first start with the Groq chip, which I just briefly described. That's packaged with a heatsink on a card, and we package 8 of those cards into a Groq node. We then package 8 plus 1 spare into a Groq rack and make that accessible in the cloud. This scale-out organization is quite unique. Number one, it takes advantage of the packaging hierarchy to make a low-diameter network. This is taking advantage of the Dragonfly topology, which exploits packaging locality. It creates what we call a software-scheduled direct network. And it allows us to really put our foot on the gas and communicate to 16 directly attached chip-to-chip links on each TSP. The scale-out organization takes advantage of a low network diameter to pack as many as 8 of our chips into a single node. And those 8 chips are connected to their 7 peers using 28 cables that are tucked in underneath the hood of each node. That allows us to richly connect up the 8 TSPs within a node to, again, take advantage of packaging locality. These nodes are connected using electrical cabling, and the longer cables will use optical cabling between racks, rack-to-rack network. The Dragonfly topology is a hierarchical topology. It first builds a group by recognizing that these 8 TSPs together each expose 4 global ports. So 8 times 4 is 32 virtual ports that are used to connect up the global system. And that allows us to connect up to 32 peer nodes for a total of 264 TSPs in a single system. We can extend this idea and make the rack our local group, in which case we'd be able to connect up to 145 racks in the system for a total scalability of over 10,000 TSPs in the system. Groq scale-out topology uses the Dragonfly to fully connect the set of 8 global nodes within the rack, as shown here in this diagram. It allows us to have a spare node to use as a hot spare and take advantage of edge and node symmetry in the network to be able to provide N+1 redundancy and improve the system resilience as a result. At the heart of the system organization is a globally synchronized network. Now, of course, the network isn't truly synchronous in that there's not a global clock going to every node in the system. We provide the illusion of synchronous behavior. In particular, we use a series of hardware and software techniques, a hardware alignment counter and a software alignment counter that allows us to detect when drift occurs and compensate for that drift. The network is composed of plesiochronous links, which means that they're mostly synchronous. They're synchronous within the tolerance of the clock and the clock crystal that's driving each link. So we take advantage of that, and we're able to detect when that drift happens and compensate for it through a series of hardware and software techniques. Again, this is an area that we had to identify and enable ISA support to be able to deskew those chip-to-chip links. So there's specific instruction support to allow us to deskew those links. In addition, links are, instead of hardware flow control, they're software flow controlled. They're paced, and software paces the links to ensure that they never overflow or underrun any of the links. At the heart of this, we rely on forward error correction so that we can have a fixed latency across every network link. And this is what allows the compiler to be able to reason about the time in flight and to reason about how long it takes for a message to arrive at its destination. Conceptually, when the machine comes out of reset, there is some initial these counters are initially independent of one another, and we bring them into lockstep. And they may drift slightly over time, but from time to time, we deskew them and bring them back into lockstep. And this is how we maintain that illusion of synchronous behavior across the distributed system. So unlike conventional networks that really have rely on a hardware arbitration scheme to dynamically contend for a set of output ports, we take a different approach in that we make all the physical network ports schedulable by the compiler. The compiler can literally schedule the network links just like it would schedule an ALU or a matrix unit. This alleviates some of the more conventional approaches that are reacting to congestion in the network. Instead of reacting to that congestion and doing adaptive routing to try to ameliorate the hotspots that result from contention, we instead take a first principles approach of avoiding the contention altogether and spreading the traffic pattern across the available path diversity in the network to expose and take advantage of the additional bisection bandwidth. One of the things that this allows us to do is to treat the tensors as a message. In other words, we're routing vectors as our packets, and those vectors occur back to back in time as a contiguous stream of vectors forming a tensor. And that allows us to frame a message as a sequence of vectors. This allows us to encode a message on the network very efficiently with only 2.5% encoding overhead. At the heart of this, we want to take advantage of both minimal and non-minimal routing. Every TSP in the system has exactly one minimal path between every source-destination pair. However, there are lots of non-minimal paths. For example, if we wanted to route from TSP0 to TSP3, there's one minimal path, but there's many non-minimal paths. And the software, the compiler in this case, can look at the size of the tensor and decide how many paths across which to spread that to minimize the serialization latency as it travels across the network. This allows us to do what's called deterministic load balancing instead of the more conventional approach of adaptive routing, adapting or reacting to congestion in the network. That has its own problems since you can only see a small sliver of the network at any one time. You're only looking at the congestive state of your output ports, and that can lead you to make a bad decision or a bad routing decision and choose a bad path that might be more congested than the one that you're routing away from. This approach has some wonderful trade-offs. It allows the compiler to load balance all the physical links, just like we would any other functional unit on the chip. At the heart of our chip-to-chip links is a simplified communication protocol and flow control. The flow control, as I mentioned, is explicitly driven by software. There's no hardware flow control. So software must ensure that they don't overflow or underflow the C2C links. And that's done, again, as a matter of principle, making determinism a first principle, a cornerstone of the design. If we look at a traditional RDMA kind of request where we're issuing a read to a destination, and that read is going to cause a memory transaction that will then flow the reply back across the network where it can later be used. A much more simplified version of this is where the compiler knows the address that's being read and the data is simply pushed across the network at the time it's needed so that it can be consumed at the source. This allows for a much more efficient network transaction with less messages on the network and less overhead. We take advantage of redundancy within the TSP and within the network and the system as a whole. For example, for yield recovery, the chip is actually constructed from 21 superlanes, of which we only use 20. So we can tolerate one bad superlane as a matter of manufacturing yield. This allows us to hide that spare superlane from the compiler. This is the one area in which we actually do hide the hardware details. It enables us to use an all good chip to be able to tolerate some amount of defects that may appear in the field. In addition, a redundant power supply and a redundant node within each rack provide additional redundancy. Not only that, but determinism simplifies and improves the ASIC design process. Design and verification can be expressed through a number of assumptions that the hardware and software need to ensure and guarantees that the hardware and software need to make sure that each other are validating. For example, any guarantees that the hardware is making need to be validated as software assumptions. The software stack plays an important role for our reliability and redundancy. Specifically, the exception handling is taken care of at the runtime level. This is why the forward error correction is needed on all the links. If we encounter an error, it requires a replay, a software replay, and that is handled through the runtime. To protect all the on-chip data structures, we use SecDed or single error correction, double error detection to protect all of the data paths, all the stream registers, all the instruction buffers and instruction queues on the chip. We call this kind of approach ECC everywhere for obvious reasons. Now that overhead is easily amortized and we can take advantage of that. And it pays to be a little bit paranoid here. As you can see, silent data corruption does happen, as some of my former colleagues from Google have published in their paper, Cores That Don't Count. It's important that we be good stewards of our customers' data. So we protect all the critical hardware structures. In this diagram, every one of these gray boxes that are numbered are the stream registers. Those are strongly protected with SecDed. And that's important as we want to, again, preserve and protect the tensors as they flow across the chip. In addition, we want to provide exception handling to avoid common things like arithmetic exceptions. Arithmetic overflow or underflow that may result is handled a priori by deciding the exception semantics ahead of time. For example, the compiler can avoid any overflows, arithmetic overflows, by using the saturating instructions like add saturate, subtract with saturate, or multiply and saturate. That allows us to avoid having a value spill over and go from a very big value to a very tiny value as it overflowed the bit precision. So if we look at our workloads that we're uniquely capable at, they tend to all be related to linear algebra, since that's the workhorse of machine learning, as well as a lot of HPC codes. To give an example of this, we look at Cholesky factorization using a block cyclic decomposition to spread the triangular elements across multiple chips. We achieve state-of-the-art results across both BERT and BERT large on the TSP, as well as demonstrate how a general matrix multiply can be done really efficiently. And then lastly, all these benefits really come to fruition when we put the pedal to the metal for communication. In particular, we see that even though we have less pin bandwidth than a competitive chip, we're able to take better use of that pin bandwidth and take advantage of fine-grained communication. In other words, small tensors can be very efficient on this network. Lastly, I want to leave you with a few summary and takeaway points. First of which is all of this was intended to enable the compiler, make the compilation process efficient and lightweight. And this is evident by the progress that the compiler has made, the rapid progress that we've made, being able to compile more generally a variety of different models that have a variety of different types of operations. So if we look at this more broadly, what we're trying to accomplish is predictable and repeatable performance that provides low latency and high throughput across the entire system. Determinism enables this software-defined hardware approach. We're not about abstracting away the details. We're about controlling the hardware underneath. And we want to do that by exposing the right set of architecturally visible state, turning that over to the compiler so that it can reason about correctness from first principles, making software and exception handled at the compile time and at runtime, respectively. And lastly, we enable this synchronous communication model, which allows us to do lock-free communication across very large systems. And that's a real superpower that we hope you'll be able to take advantage of. Thank you for your time and thank you for your attention. We hope you'll reach out to us at Groq, and we are hiring if anyone is interested.
Dennis. Well, the the deterministic execution is clearly one of the most unique aspects of your architecture, and we have a number of questions that touch on that topic. I'm going to try to combine 4 of them actually, and then give you a chance to reply to those. So the first question from Deepak Unikrishnan from NVIDIA: do you support conditional execution, and how does that affect determinism? A question I think is a little bit related from Yashwardhan Narwane from NVIDIA. Are there compiler methods to bypass one or more execution stages? And then there's a couple questions that kind of highlight some examples from machine learning that may introduce non-determinism. So Zhao Yu Ma from Google asks about sparsely activated ML models that trigger a part of a neural network based on runtime values. And he also asks about variable DRAM latency. And then Cliff Young from Google asks about how embeddings are handled, and that those would seem to have dynamic access patterns and load balance issues. So Dennis, if you could address that general topic of determinism.
So let me tackle some of those. So determinism, the first question around dynamic execution and branchy behavior is really best handled by our predicated execution. The vector unit has predication in it so that you can execute code that does have branches in it. And unfortunately, this is one of the trade-offs, right, is to be able to enable predication, you're throwing away half the branch in some sense. So you're making a explicit trade-off at how you want to do kind of branchy behavior and how to handle that, and reducing the complexity of it also entails some overhead. And so for branchy behavior, that's how we handle that, is we can, a variety of techniques. First and foremost is predicated execution. There's also the ability to, the compiler can dispatch small little basic blocks. Think of them as tiny little micro models that exist on the chip, and then we can dynamically dispatch those, kind of like a basic block, where you have a basic block that's sitting in memory as the resident sets growing, and you can dynamically dispatch that. So that's a way that we kind of deal with some of the dynamicism that arises in machine learning models. One of the areas that we had to account for was that there is some non-determinism, in particular around I/O, right? The PCIe it has I/O. It's essentially attached to the host memory adapter, and that host memory adapter has to contend with threads from the host. And so there is some ability to absorb and tolerate that non-determinism. Once we move the data and program onto the chip, however, it operates deterministically at that point. So there's kind of epochs over which we can describe the deterministic behavior and then tolerate some amount of non-determinism in the face of what is asynchrony from I/O and asynchronous events like exceptions. And so we had to deal with some of that to be able to tolerate it. And that's where these synchronization techniques come into play.
Yeah, thank you. So Cliff Young from Google asks, will we see an MLPerf submission by Groq sometime soon?
I hope so. And we're a startup company. We've been very, very busy working with our flagship customers, working to bring value there. And as we grow and as we have scaled to be able to compile more and more models, we intend to submit to MLPerf. But as a startup, that has been a difficult point to staff up and tackle that as we have to trade off all the other kind of real world things around a startup has to balance.
Umar Dabaz from NVIDIA asks, could you elaborate on how bidirectional instruction flow helps capture locality?
Sure. So I want to clarify something. So instructions are dispatched on the chip from south to north. So they're executing in this kind of cycle by cycle manner, and data is flowing east and west on the chip. And so we take advantage of that kind of data pipeline that's set up, that tensor assembly line, so to speak. And as data is produced by one of the adjacent functional units, we can pass that output to one of its downstream functional units to take advantage of what is classically known as chaining, for example, vector chaining, to be able to tie together your outputs from one to the inputs of another so that you don't have to go back to main memory to write the results and then fetch it from main memory. So you can do all of that without burdening and putting additional main memory pressure and without additional loads and stores to main memory. So we can take advantage of all that locality, that data flow locality, for lack of a better word, and chain those functional operations very, very efficiently with only a single cycle delay between them.
Thank you. I think that's all the time we have right now. Thank you for the talk. And there's a few more questions in the Slack channel if you're able to get to those. But thanks very much. Okay, the next talk up is from Boqueria on their next generation at-memory inference acceleration device with over 1,000 RISC-V cores. There's two speakers, Robert Beachler and Martin Snelgrove. Bob Beachler is the Vice President of Product at Untether AI, a Silicon Valley veteran and proven senior executive with industry leaders such as Altera, Xilinx, and BrainChip. He brings to the company a wealth of experience in the development and marketing of FPGAs, software tools, vision processors, and artificial intelligence acceleration devices. Martin Snelgrove is the co-founder and chief technology officer at Untether AI. Dr. Snelgrove has held progressive roles at product and design services firms at scale. Prior to this, he spent many years in academic R&D, leading to the commercialization of products in digital signal processing and mixed signal processing, and he's widely acknowledged as a pioneer in this field. Dr. Snelgrove is an author of 36 patents and over 100 refereed publications. So let's go to the talk.
Hi, welcome to Hot Chips. I'm Bob Beachler, the Vice President of Product here at Untether AI, and I was the Acting VP of Hardware Engineering during the development of Boqueria. With me here today is
Martin Snelgrove, CTO and a co-founder.
You know, it's amazing that it was only 10 short years ago that the AlexNet paper came out and started the current AI summer. Since that time, we've seen an explosion of neural network architectures. Untether AI was founded in 2018 in order to come up with a new method of compute in order to provide the efficiency and the throughput necessary for today's AI workloads. In 2020, we introduced our first generation of devices, the Run AI 200, which offered 500 teraops of performance with an efficiency of 8 TOPS per watt. Here today at HotChips, we're introducing our next generation device, Boqueria, which offers 2 petaflops of inference acceleration with an amazing 30 TOPS per watt in energy efficiency. AI inference presents 3 key challenges to the developers of chips. 1, the increasing computational requirements and the power efficiency necessary for these AI workloads. We're also seeing a tremendous explosion in the architectures of neural networks, and you have to have the flexibility to be able to adapt to the changing neural network landscape. And finally, and particularly in inference, you want to make sure that you're doing things as efficiently as possible and using the right data types to ensure the necessary accuracy, but at the same standpoint, providing energy efficiency. So therefore, what we have done is to develop an architecture that is the right mix of coarse-grained architecture to be able to provide the compute performance, and also interleaved with that, the types of data types necessary for both efficiency, but also to ensure the accuracy. Accuracy is critical because it can cost millions of dollars in the case of recommendation engines. In fact, McKinsey says that 35% of Amazon's revenue is based upon their recommendations. Also, when you start looking at ADAS and autonomous vehicles, accuracy is critical because it can cost injury and lives if the accuracy is not maintained. Okay, when we sit down to architect our AI inference acceleration, the first thing that we saw is that 90% of the energy in doing neural network compute is in movement of data, either from external memory or on internal caches, and only 10% is really done in the compute. So what we've done at Untether AI is really to turn that upside down and make sure that we are being as efficient as possible in our data movement and put the compute where the data exists. We also architected our architecture to have the right amount of compute at the granularity level necessary and specifically tailored for acceleration of neural networks. And then finally, we've done a lot of research in the different data types in order to ensure accuracy. What we found is that FP32, which gives you the ultimate accuracy, requires too much compute. And you can get the same level of accuracy with a BF16 data type, but we've also found that we've developed a new FP8 data type that quadruples the efficiency from BrainFloat 16, but at the same time preserves the accuracy necessary for today's AI workloads. At Untether AI, we're pioneering at-memory compute, where we place the compute element directly attached to memory cells. We feel this is the sweet spot for AI acceleration. If you look at traditional von Neumann architectures, that's where you have all of the energy expenditures and data movement, moving from DRAM, having large hot caches on chip. Now there's also in-memory compute where people are trying to use the memory cell in order to do the fundamental multiply accumulate function. While this provides very low energy, all the supporting circuitry around it in order to compensate for the analog effects, as well as all the digital logic you need for the other non-MAC functions, ends up degrading the actual performance improvements you see within memory compute. Whereas at memory compute, we use a standard digital logic process, we use standard SRAM cells, but we provide tremendous energy efficiency because we have a very short distance for the data to travel from the storage cell to the actual compute element. So here at HotChips, we're pleased to introduce Boqueria. It's a 2 petaflop, 30 teraflops per watt at-memory inference accelerator. We can do this because of our innovative at-memory compute structure. Each of our memory banks, of which there are 729 per chip, each has a dual RISC-V processor. We run these at 1.3 gigahertz using a TSMC 7 nanometer process. Because we place the processing elements directly attached to memory, that gives us our energy efficiency on the order of 30 teraflops per watt. There's 238 megabytes of SRAM on a given chip, And because the processing elements have their own dedicated memory, we have tremendous memory bandwidth, on the order of a petabyte of memory bandwidth. The device is ultimately scalable. We have direct chip-to-chip interconnect using PCI Express so that we can place multiple chips together in order to expand to the largest natural language processing networks. Also, because it's a spatial architecture, we can make smaller devices using less memory banks. We support multiple different data types from integer 4 up to BF16 for the utmost in compute accuracy.
So let's look at that memory bank. Smart memory, it's computing memory. Those two RISC processors actually each run 4 row controllers, and the row is really the locus of control for this thing. So we have a whole control hierarchy, 729 banks, 2 RISCs each, 4 subcontrollers in each one. And each of those controllers is running a 64-element SIMD machine. Now, there's your hierarchy of control to go with the huge number of threads that are in a typical neural network. And now on the side of connectivity, you need connectivity within a row. And there we have a thing called a rotator cuff, which we can configure as we like to do nearest neighbor communications within the row. And so you can rotate things around and permute them and so on, so that each output result can see each input activation value. That's within a row. Next level of hierarchy up is a network on chip. So the row controller can do a send or do a receive on a socket. And there's a background network we'll talk about that takes care of that. But from the point of view of the row, it can send data at a 70 gig rate north or south, and at a 7 gig rate east or 7 gig west. And that's not our system rate. That's what an individual row of our 6,000 rows can handle. Let's move down into the processing element. That's where the real at-memory side of what we're doing happens. That's where we have the data for all the coefficients, and that's where the actual number crunching happens. So there's the memory, first of all, and it's a low-power, high-density static RAM array. We use standard bit cells, but we use them better than you'll see in a typical SRAM, because we know exactly the pattern in which we're using data. So we don't do a fetch without using the data, and we swing the data the least we can to get efficient communication. And that SRAM bolts pitched matched onto a processing element that's computing a value. So if you have a 64-element vector, each processing element is computing one of the output channels, would be a typical use. And so inside that processing element, well, it's basically a multiplier accumulator and some masking technology so that you can get conditional execution, just as you do in any other SIMD machine. And that processing element has as its 2 inputs a coefficient from the SRAM and an activation that's from this rotator cuff. And on each cycle, you can grab a new value from the memory, grab a new input, and update your output. There are also some temporary registers, and there's a network on chip connection there. That processing element is basically built for 8-bit floats, but as a subset or by using it multiple times, you can do int 8s, BF16s, and single time you can do int 4s. Lots of power saving features. If an activation is 0, nothing clocks. There's support for structured sparsity, a 2 out of 4 kind of structured sparsity technique. And all of what I've described, from a MapReduce point of view, you'd call a map function. That is, I've been describing local operations within the PE, but there's some reduce functions, such as you need for softmax, where you have to add up all the values in a vector, or layer norm, where you're doing overall statistics in a vector. And for those kinds of things, we have a reduce layer that computes a sum or a max and pumps it back to the controller. All of this stuff is connected together, built entirely about energy efficiency. So communication with this cuff is adjacent to adjacent, and the knocks are all minimum distance travel. So that 8-bit floating point, we optimize it for inference, not for training. So the picture here shows sign bit and 3, 4, or 5 exponent bits, and your choice of 4, 3, or 2 mantissa bits to go with that. And for training, you typically want to go with more exponent, less mantissa. For inference, you want to go with more mantissa, less exponent. It's about getting precision results. So we've optimized for the inference side, and we're using FP8 instead of the int style. We're getting twice the energy efficiency and tighter die size with floating point relative to integer 8 at essentially the same kind of precision. So for accuracy, relative to FP32, if you use BF16 mode, you get essentially perfect results. If you use FP8 mode or int8 mode, you get similar results, but in FP8, we're getting 4 times the throughput because there's essentially only a 4 or 5-bit multiplier relative to the int8. Now moving back up to the RISC-V level, it's a standard RISC-V with additional instructions focused on those processing elements that we saw. And those instructions do things like GEMV, they do reduce and so on. So there's this collection of instructions, each handled with a state machine in the particular controller, so that those engines can go and grind by themselves while the RISC moves along and handles the multiple threads. Each of those RISC processors sits there thinking that it's running natively C. It just has these command queues it can fill up. Each one has 6K of local memory, a 32-bit ALU with things like a 32-bit multiplier that you use to aggregate row kinds of functions. So if you're doing something like softmax, you're doing the reciprocal, for example, would be done in the RISC, and all of the exponentials and so on would be done locally. Going back up again now to the chip level, we talked about the 70 gigabyte per second north-south, for example, network on chip. That aggregates, that's all pipelined so that all of these rows are capable of throwing stuff onto those network interfaces at full speed. So you end up with nearly 2 terabytes per second in each direction aggregate. There's also a NOC that goes around the periphery of the chip to all of the I/O devices. That gives you another 140 gig in each direction to get to LPDDR and PCI Express and so on. And that NOC is not an off-the-shelf NOC. It's a NOC that's first of all designed for energy efficiency. Data gets sent the minimum possible distance, meaning at the minimum possible energy in any XY pattern that the manager chooses to set up. And the model from the point of view of the RISC processors is a circuit switch model. All that they do is throw data onto a socket or pull it off a socket. Externally, those things are wired together. The 6K of code in each RISC doesn't have to worry itself about connectivity. So talking about the input-output, there's by 16 Gen 5 PCI Express, that's 63 gigabytes per second, that gets you back and forth to a host. And we also have by 8 PCI Express that we can use for chip-to-chip connectivity. So you can scale this thing out to as many chips as you like. And that socket interface I mentioned, there's absolutely no difference in how the code looks, whether it's transmitting chip-to-chip, on-chip to a neighboring row. So that's how it scales out to infinite chips, and each one of them has this multi-level memory architecture. So there's 200 odd meg of memory just directly in those processing elements. We have some scratchpad memory for things like temporary storage of activations for layer norm and so on. And if that on-chip scratchpad and the on-chip in processor memory isn't enough, there's 32 gigabytes of LPDDR5 that you can get to.
So what Martin just described is the beauty of our spatial architecture. And this provides us some scalability benefit. we can reduce the number of memory banks that we have on a given chip to fit different form factors and power energy envelopes. So within our Boqueria family, we'll be scaling from sub 1 watt devices all the way up to the B4 infrastructure class device that we described. This allows us to address multiple different price performance points and form factors. We'll be having a series of cards scaling from single wide M.2 all the way up to PCI Express. And as you saw, we have a very flexible I/O ring, and that makes it chiplet ready, so that for those that want to integrate directly die to die within it with SoCs, we have that capability as well. So let's talk about our PCI Express card. We're going to be able to fit 6 of these Boqueria devices onto a single PCI Express card, giving us a tremendous amount of SRAM capability to be able to scale to the largest language models. And with our chip-to-chip and card-to-card interconnect, we can now make very powerful server implementations. We also have the external LPDDR5 giving us a tremendous amount of storage on the chip. So overall, we have this scalability feature to allow us to provide the utmost performance as well as energy efficiency in a standard PCI Express form factor. Now, the silicon is only as good as the software that supports it. Our Imagine software development kit provides an automatic graph lowering capability to take neural networks from common machine learning frameworks like TensorFlow and PyTorch and reduce it into the kernel code that runs on these RISC-V processors. We provide a model garden of pre-created neural networks, but the majority of our customers have their own neural networks that they've already trained. We provide automated quantization capability to reduce it into the data types required. We do the compilation and mapping to the kernel code. We do physical allocation in terms of placing those kernels onto the silicon and interconnecting them automatically. We have a suite of analysis tools where you can see floor plans, you can see code profiling. And then finally, once we have our programming file, we can put that into our chip, and it's controlled through an easy-to-use runtime that has a C or Python-based API to allow it to be integrated into the rest of your ML operations frameworks. Now, our spatial architecture allows us to do something very unique. Normally, you would take a graph and run it sequentially on a CPU or a GPU, but we have the ability to replicate layers. So when we look at a neural network, we'll look at the bottlenecks and maybe replicate a layer or even a subgraph. We can also run entire neural networks in parallel on our chip. So we use this capability to fine-tune the networks to utilize the right amount of resources to hit the performance targets necessary for a given application. So it's the combination of the software and the silicon architecture that really brings out the benefits and efficiency of at-memory compute. With Boqueria, we've hit a new milestone at 30 tera operations per second per watt. At the same time, in a single PCI Express card, providing up to 12 petaops of performance. That's more than 5 times more than what's available today in terms of petaflops per card and a 7x increase in energy efficiency. It's our energy efficiency that provides us with our throughput. Because we can pack more compute into a given form factor and a given power envelope. If you look at the ML perf benchmarks, we're on the order of 15 to 80 times more throughput for these types of vision networks. And as you heard from Martin, we have dedicated circuitry for attention networks. So when you look at a natural language processing network like BERT-base, we're on the order of 8 times greater throughput and 15 times greater in terms of the energy efficiency when you measure queries per second per watt. So with Boqueria, we're solving the 3 key challenges that I talked about at the beginning of the presentation. First of all, its at-memory compute structure provides unrivaled energy efficiency, which drives the ability to increase the throughput and acceleration of neural networks. It's a scalable spatial architecture so that we can make smaller devices and larger devices, and we can interconnect them together in order to scale to the largest natural language processing models. And because we've selected the right level of compute granularity, we can support today's neural network architectures and be future-proof for future neural networks. And because we support multiple different data types, the user can trade off between accuracy and throughput for their specific application. Thank you for attending our Hot Chips presentation. At this point, we'll open it up for any questions that you might have for myself or Martin.
Okay, thank you, Bob and Martin. I'll start off with a question from Sabarish Ravikumar from Waymo. He says, congratulations, and these are some impressive perf and perf per watt numbers. Will we see an ML perf submission at some point?
Sure. Thanks for the question. And, as the previous session at Groq said, as a startup, we focus on solving our customers' issues first, and ML perf is next. So yes, we have every intention to do so, but it's really a resource issue in terms of when we're going to get to that point that we have the bandwidth to be able to submit there. It's on our roadmap, but it's not imminent.
Okay. Kevin Cruel from Tirias Research asks, are you considering stacked 3D SRAM memory in the future?
Martin, would you like to take that? Go off mute.
No, that's a corporate question, Bob. I'll leave you to handle that one.
Well, so thanks for the question, Kevin. So, we're an at-memory compute company, so we're constantly monitoring new innovations in memory technologies. And we'll use the appropriate type of memory technology that we feel is manufacturable at scale. Today, that's with on-chip SRAM, but in the future with stacked die, as that becomes more manufacturable and cost-effective, that's certainly something that we can analyze and entertain.
Okay, Cliff Young from Google asks, how are instructions supplied to the RISC-V cores? Do they just run out of the 6 kilobytes of local SRAM and code must be managed manually?
Martin, would you like to take that?
Sure. And I wouldn't say manually, it's the compiler's job, usually. So the compiler takes PyTorch or whatever you start from and chops it up into 6 byte. I was going to say bite-sized pieces, but 6K bite-sized pieces, and distributes them in the system. You certainly can code that stuff up manually if you want, but normally it's easy enough to do systematically. 6K is actually pretty big. The threads we're running need to run very fast, and there just isn't time to use all 6K in most applications.
And I guess following on the topic of the RISC-V, Sabarish Ravikumar from Waymo asks, are you able to share what RISC-V processor was used? Is it open source or homegrown or licensed?
Yeah, it's a custom designed processor. We start with the RV32 EMC instruction set, I think as is shown in Martin's slides. But we've custom implemented that. Because we have so many of them, it's very important that we do it as the most efficient way possible. Also, with the 20+ custom instructions that we've designed specifically to take advantage of our architecture and inference workloads, that's also all custom circuitry that we've developed and extended the standard RISC-V instruction set to be able to utilize our architecture and to optimize for inference workloads.
Okay, next, Axel Chevalier from Next Silicon asks, what is the power of the 6-chip PCIe card?
Sure. Well, we're going to design that for what we call 100% GenV, which is the worst case maximum operating, and that'll be around 400 watts. We typically see, however, that when the actual inference workloads are being run, they run at about half that power consumption. So we'll over-design it, obviously, from a power supply and cooling standpoint. But typically, we'll see workloads running in the 200 to 300 watt range.
We have a question from Asit Mishra at Apple. What kind of structured sparsity is supported?
Martin, why don't you take that?
Sure. So basically 2 out of 4. So the you have a register with a coded
value that says which of the four activations any given, or which of a group of four activations any given coefficient is going to hit, and pairs of coefficients share that.
And you get a performance speed up from that?
Yeah, it's 2x. If you use that, you get 2x power 2x cycle and 2x model size. It's a 2x win on everything.
I will interject that the TOPS numbers that we show do not include structured sparsity. So you would multiply by a factor of 2 if you were to take advantage of that.
Next question from Ashutosh Dar from NVIDIA. What is the treg file and what is its size?
So I'll do that one, Bob. So
yep.
I think Walid stuck in a partial response in the Slack, but it's temporary registers. It's a couple of registers per processing element, and it's just a traditional way you'd use a register. It's a fast place to store a temporary value. You can store stuff in memory. Memory is a little slower. You can even use the network on chip to store stuff. Send messages to yourself if you like. So there's expansion space available. When you want a single cycle quick place to put something, the temp reg is the place to put it.
Thanks. Yeah, I think that's all we have time for right now. So thanks very much for your talk.
All right. Thank you.
Thank you.
Thanks, folks.
Okay, next up, we're going to go into a sequence of 2 talks on the Tesla DOJO architecture. The first talk is on the DOJO microarchitecture, the microarchitecture of Tesla's Exa-Scale computer. The speaker is Emil Talpes. Emil is currently the chief architect of Tesla's DOJO compute solutions from the D1 chip to interface processors. He joined Tesla in 2016 and has worked on the FSD neural network accelerator before moving on to architecting DOJO chips. In his prior life at AMD, Emil had multiple roles from CPU performance modeling to RTL and architecture. He delivered multiple CPUs spanning from the Bulldozer architecture to Zen and K12 families. Emil has a PhD in computer engineering from Carnegie Mellon and a bachelor's in computer science from the Polytechnical University in Bucharest. So let's go to the talk.
Thank you very much for your introduction. My name is Emil Talpes, and I am going to talk to you about the microarchitecture behind DOJO. DOJO is an in-house system built at Tesla, and its primary purpose is to service our internal learning workloads. When developing this system, we have had 2 primary requirements. First, we want it to be general. We know what we are building today, we know what applications we are running today, and we can analyze them. We could potentially build a special hardware dedicated to these applications, but what we also know is that these applications change a lot, and the machine learning is a new field. It changes very fast, and next year most likely we will run a different set of applications with different characteristics. We also want the system to be very scalable. We already run extremely large models, and our models keep growing all the time. So with this, we want to build something that can scale very far, and it has to be general. We want it to be optimized for what we know that we are running, but we want it to be general with some general purpose, with some specific with some specific accelerators on top. With that, we are building a distributed system. What is a distributed system? At the bottom, a distributed system is a hierarchy of nesting boxes. At the bottom of the hierarchy, we have a CPU, which describes the typical characteristics of the system and the programming model of the system. Multiple of these CPUs are put together in a die. They are very tightly integrated, and many times that actually means that they are sharing components. Sometimes they are sharing caches, sometimes they are sharing accelerators. On top of that, we build modules, and on top of modules we build boards, and then racks, and then cabinets, and then we scale up to the entire system. Integration tends to get looser as to go outward, and that means at the system level we tend to see lower bandwidth between components and higher latencies. Such a system is described by 3 models. One is the compute, which describes the architecture of the basic block, describes the architecture of the CPU that constitutes the bottom of the hierarchy. The communication describes how these nodes, how these CPUs talk together, and the synchronization describes how they can actually operate together in a sensible way to perform a single task. A scalable system requires a basic block that can function as a standalone. So our basic block is a fully fledged computer. We have a high throughput general purpose compute node which has a multi-instruction data path. It can execute several instructions in parallel, and it can also execute several threads in parallel at the same time. The CPU is relatively powerful, but our optimization point tends towards math-heavy application instead of control-heavy code. The processing pipeline starts with a 32-byte fetch window that can hold up to 8 instructions, which are fed to an 8-way decoder. The 8-way decoder feeds a 4-way scalar pipeline which can execute 2 integer instructions and 2 address generation operations per cycle. At the other end of the pipeline, we have 2-wide vector scheduler with 1 pipe dedicated to matrix multiplication operations and another one dedicated to typical SIMD instructions. Throughout this entire pipeline, we support multiple threads in parallel, but our SMT support is mostly geared towards running a single application with multiple threads which allow the compiler to expose parallelism to the hardware. We are not focusing on running completely independent applications through the same pipeline. We don't have virtual memory, we don't dedicate hardware for protection mechanisms, and in many cases we expect the software to actually manage sharing resources between threads. For us, a typical application utilizes 1 or 2 compute threads and 1 or 2 communication threads per node. To make the system scalable, the processing node has to have enough memory to be able to execute code out of its internal memory without reaching out to the external portions of the system. For us, every processing node has its own memory, which is high enough bandwidth to feed the data path. We support 3 64-byte loads per cycle and 2 64-byte stores per cycle. The loads can be streaming, or they can be in a gather organization. We can gather 8 bytes or 16 bytes granularity from the internal SRAM. From the external SRAM, data has to be first explicitly copied into the internal SRAM before the application can have access to it. We also support a side port for a list parsing engine. The list parser can provide instruction immediate constants from a precompiled database, which essentially allows the programmer a free level of indirection instead of having to use a dedicated load and then a processing and then an extra load to access the data. We'll come back to the list parser engine in a few slides to explain how this can be leveraged to create efficient software routines. Every compute node has a network interface which has direct connections to its immediate neighbors, east, west, north, and south. To make the system very scalable, the network interface offers extremely high bandwidth. We can move 2 packets per cycle in every direction to each neighbor. And the router has direct access to the internal memory, and that allows the network to move data from one memory to another without interrupting the processing pipeline. The network can pull and push data from the immediate neighbors in a single cycle, and going to further away, it adds more and more hops. Our data path is organized like a funnel. In the front end, we can execute we can decode and execute 8 instructions. Some instructions can be executed and dropped out of the instruction stream right there. Such instructions are looping constructs, list parsing operations, or predication based on this kind of constructs. On the scalar side of the pipeline, we execute 4 instructions in parallel, and we can do regular integer code, branches, or address generation operations. This typically takes care of the control part of our application. We also execute the network synchronization primitives on this side of the pipeline. Once we get to the bottom of the pipeline, the vector pipeline, we typically execute regular SIMD operations. And we have two pipelines. One executes matrix multiplications. The other one just executes SIMD operations. Why does it make sense for us to have a funnel-like pipeline? Why does it make sense to build a pipeline that is wider in the front end versus the back end? Well, this is an example that shows how we can execute a relatively complicated concat operation across multiple axes. For DOJO, that typically means reading data out of several source nodes into a destination node and lining it up before we start computing. In such cases, the compiler would just list the addresses where the data comes from and the number of packets and pack them together in a database that is placed in the SRAM. It also generates a snippet of code that parses over this database. Most of these instructions that are presented in this code snippet actually don't have to go to the execution backend. A lot of the code is organized around these looping constructs and database operations, predication, and all of those can be dropped in the front end. So in the backend, we actually see very few instructions. Using multi-threading and these kind of constructs, we can put together several short compute sequences and then run them asynchronously as like little widgets that we assemble together in the system. The instruction set, as I mentioned, is organized in three categories. We have very few instructions that can execute in the front end, but they tend to be very commonly used in applications run on DOJO. We have a 64-bit scalar pipeline, which deals with all the scalar instructions and memory operations. And we have a 64-byte wide SIMD application. Most of our specific machine learning functionality is concentrated on the SIMD side of the machine. On top of the typical instructions that you find in any SIMD processor, we have specific operations which are targeted towards machine learning. We have 8x8 matrix multiplication instructions with inline support for various operations like loads and gathers. We can transpose the operands on the way into the data path, and we can expand operands if we are running depthwise convolutions. We have a specific set of shuffles which are geared towards these particular algorithms. We can do transpose and convert instructions from one format to another. We can also do stochastic rounding on wide data, convert it to a narrower format, and we can do implicit 2D padding. Our data path can seamlessly execute all the typical integer data formats plus an assortment of FP formats. It all starts with FP32. FP32 is the gold standard for all these machine learning algorithms, and it can be used for anything in these algorithms. But it can also be overkill in some cases because it has more range and more precision than most of these applications require. For this reason, some architectures have started using IEEE FP16, which has a higher representation density, but in some cases it doesn't have enough range to cover all particular use cases. So for that, other applications have started using BFP16, which has more range, but at the expense of a much sparser coverage density. DOJO adds what we call configurable FP8 data type, where we can introduce a programmable bias. That programmable bias allows us to shift the representation range from very small numbers to larger numbers and allow the application to pick what exact representation range it needs based on the local needs. This CFP8 can be used for parameters and it can be used for activations as well, but there are still use cases where the CFP8 doesn't have enough precision. For those cases, we have introduced what we call CFP16, which is an extension of IEEE FP16, by adding the same programmable bias that we used in CFP8. CFP16 has the same range of representation as CFP8, but at a much higher precision and at much higher precision. This, together with stochastic rounding, allows us to quantize numbers which we would typically represent in FP32 down to this format to improve our representation density and our memory utilization. The application can seamlessly pick between FP32, BFP16, CFP8, and CFP16 for every layer at any time. Up to 16 data types can be used by the application at any time with the granularity of 1 64-byte packet. With that, we get to our first integration box. We put a mesh of 18 by 20 such CPUs together, and we create what we call a D1 die. This contains 360 teraflops of compute and almost 450 megabytes of SRAM, all put together in a die which is 645 square millimeters. Around the compute mesh, it has a ring of serial links which allow seamless connections to the neighboring dies. This allows 2 terabytes of bandwidth across each edge on each direction. Our second integration box is what we call a DOJO training tile. To achieve that, we take 25 dies which have been pre-sorted and verified to be good, and we assemble them together in a fan-out system. One of these systems has a 4.5 terabyte of tile bandwidth, and like the die before, it has seamless connections to the neighboring training tiles. Inside, all interconnects have been scaled up to the limits of physics, and they occupy all tracks on the X and Y dimensions, so the electrical and cooling solutions have to be provided vertically. With this, we can create an entire DOJO system. We just take multiple of these 5x5 training tiles, and we place them next to each other in a 2D mesh. Around the mesh, we place what we call the DOJO interface processors. DOJO interface processors provide connectivity to off-the-shelf host systems as well as shared memory support. Each interface processor supports connections to 32 gigabytes of memory to a total of 160 gigabytes of shared DRAM per host processor. So with that, a training tile connected to a set of interface processors will have 11 gigabytes of highly distributed and high bandwidth internal SRAM and 160 gigabytes of shared DRAM with lower bandwidth but much more contiguous, and the compiler get to allocate all of that. To communicate across all of this system, we have our 2D mesh. At any point within the die, the bandwidth adds up to 5 terabytes of cross-section bandwidth in each direction. As we integrate more and more of these processing nodes, we will hit discontinuities at a different level because of limits of physics. The first discontinuity we see at the die boundary, where we see a reduction step from a 5 terabytes within the die to a 2 terabyte on that interface within the module. Once we get out of the module, out of the training tile, we see another step down from 2 terabytes down to 900 gigabytes from each die to the neighboring die on a different tile. On the edge, every host is connected using 80 PCI links to a total of 160 gigabytes of bandwidth. Each of these interface processors also has an Ethernet access. They can reach out through to other interface processors through an Ethernet switch, and the packets that arrive into the interface processor using the regular 2D mesh can hop over to another interface processor through this Ethernet system. That creates effective shortcuts through the system. Why does it make sense to have some shortcuts through the system? Well, it turns out that in a 2D mesh, long routes tend to be expensive. Bandwidth decreases for us as we go on a long route. Within the die, the bandwidth stays constant, but immediately as we go out of the die, we see a reduction, and then going out of the tile, we see another reduction. And long routes tend to span multiple of these integration boundaries. In terms of bandwidth, the shortcuts also offer a clear benefit. A packet that happens to traverse 10 hops occupies 10 links instead of occupying a single link for a packet that just goes to the neighboring die. And on each link, it can stay for at least one cycle. This creates very strong incentive for software to keep all communication local and to build the data parallel instances as small as possible, ideally limited to a single processing tile. Every node can move data in and out of its own SRAM. It can push the data to an external memory, or it can pull data from an external memory into its own SRAM. But in some cases, it's much more efficient to use some bulk communication primitives. For that, we have DMA state machines, DMA engines on the interface processors, and we can execute contiguous transfers from the DRAM to the local SRAM, or outside from the SRAM to the DRAM, either contiguous or strided within 3 dimensions. For SRAM to SRAM transfers, we support memory region transfer, so we can tell the network to move an entire region from one SRAM to another one, or we can just do a push broadcast, which means copy a single piece of memory from the local SRAM to multiple nodes within a single D1 die. For even more complicated operations, we can put together examples, as I showed earlier, based on the list parser engine, where we can transfer data from multiple nodes source to multiple nodes destination. The network implementation is geared towards simplicity. In order to achieve high scalability, we are not building virtual memory. The entire memory and system organization is exposed to the software. The software needs to know, the compiler needs to know where every piece of data is, and in order to reach for it, it needs to specifically utilize the die address, the node address, and the local address within the destination node. The routing is simple as well. Across all functional dies, the routers are supposed to be working correctly. And that means reaching a destination is as simple as following the row all the way to the target column and then going up or down on the column to get to the destination. To make it more flexible and to allow for different routes in case of necessity, every die provides access to a routing table. As packets go in the die, they access the routing table, and they can either continue on their default route, or they can turn to a different route to go around either very congested portions of the network or parts of the machine which have happened to not work properly. The network guarantees the packet delivery. Once a packet is sent to the local router, it is guaranteed to reach its destination. On the other hand, the network does not guarantee end-to-end ordering, which means that at the destination, the application cannot start using the data as it reaches that node. The data has to be counted, and only after all the nodes are, only after all the packets have been received, we can start using the data. To count packets, we use the first synchronization mechanism, which is our counting semaphores. DOJO implements counting semaphores in hardware, and we provide all the atomicity by construction in hardware. We use these semaphores, these counting semaphores, both for counting packets arriving through the network, and we also use them as mutexes to synchronize access to shared data structures, or to synchronize producer-consumers kind of relation across either the single node or multiple nodes in the system. The second synchronization mechanism that DOJO offers is the barriers. DOJO builds barriers using a tree implementation. ARM messages travel up from the leaves towards the root of the tree, and then the ground messages travel downward from the root towards the leaves. In this example, the blue nodes, together with the red nodes, have to be part of one synchronization domain, while the yellow nodes and the red nodes are placed in a different synchronization domain. For this, the compiler just sets up a tree that spans this set of nodes, and then the application starts running. As a node reaches the barrier, it executes what we call a BARM instruction, which triggers an ARM message going up the tree. As more and more nodes reach that point in the program, they all start generating their own ARM messages, which propagate up to the root. Once the root reaches that same point, the ground messages start propagating downwards. And once the ground messages arrive at every node, then the barrier is considered satisfied. To conclude, we have gone through the architecture of the basic CPU, which sits at the backbone of DOJO. We have gone through how these nodes communicate together, and how the synchronization works in order to make everything operate together seamlessly. The defining goal of our application is scalability. We have de-emphasized several mechanisms that you find in typical CPUs, like coherency, virtual memory, global lookup directories, just because these mechanisms do not scale very well when we scale up to a very large system. Instead, we have relied on very fast and very distributed SRAM storage throughout the mesh, and it is backed by an order of magnitude higher speed of interconnect than what you find in a typical distributed system. And before I end this presentation, I would like to thank the entire team of Tesla, who has helped put all of this together and has worked on these systems for the past few years. Without them, none of this would have been possible. Thank you.
Okay, thank you, Emil. We have a couple questions about the ISA. Ashutosh Dar at NVIDIA asks, do you have a fully custom ISA, or are you running a modified RISC-V or ARM? And similarly, Nathan Brookwood asks, why did you invent your own ISA for DOJO?
Well, on the scalar side of the machine, we have borrowed some of the instructions from RISC-V, at least some of the encodings. We have added a bunch of them ourselves. On the vector side, we have mostly implemented our own part.
A question from Umar Darbaz at NVIDIA. Is the CFP bias global state, or is it tracked per variable as part of the format?
It is tracked per data packet. A data packet is 64 bytes, so instructions in the program can associate a different bias and a different type with every 64-byte packet.
Adam Butts from DE Shaw asks, is DOJO still in hardware debug or bring up, or is it in production use at Tesla?
We've had hardware for a while, and we are running it in the lab. I can't go into too many details on that.
Sure. Next question from Sabarish Ravikumar at Waymo. You mentioned data has to be copied from external SRAM to internal SRAM before being consumed. How about instructions? Can it be cached from global memory?
We do not have hardware caches, so code has to be copied the same way as data.
I see. Asit Mishra from Apple. Are there any prefetch instructions in the ISA? How is the machine hiding and overlapping compute latency with data movement?
It's all based on software prefetch. So program has to bring the data into the local SRAM, and it can use that. For that, it can use dedicated threads. That's actually the big reason why we have 4 threads in the machine. Usually 1 or 2 threads are used for bringing data from outside as prefetch.
Okay, thank you. Samantha Hirsch from NVIDIA asks, given the execution pipeline, can you simultaneously schedule scalar and vector instructions? If you're
Yes.
facing back pressure on the scalar scheduler, will the vector data path also be stalled?
The vector data path trails the scalar instructions. So usually instructions go through the scalar part of the machine, and then vector instructions keep going forward to the vector processor, the vector scheduler. This allows us to execute the scalar instructions first. Now, if the scalar part of the machine backs up for whatever reason, then whatever vector instructions were older in the program will keep executing, but we can't go and execute newer instructions. So the out-of-order part of the machine works such that always the scalar instructions execute first and the vector instructions execute later. If the scalar instructions back up for some reason, then the vector instructions back up behind them.
Right. Mark Tremblay from Microsoft. The CFP8 has the same throughput as BF16, while one might expect 2x. In addition to saving memory space and bandwidth, do you save power by using CFP8?
Yes, it would consume less power. We did not optimize specifically for FP8 in this particular iteration.
And one last question, Ramesh Narayan Swamy from Synopsys asks, what integer data types are supported?
We support pretty much everything. We support int64, int32, int16, int8.
I see. Okay, there was a lot of interest on the Slack channel, so maybe you can answer a few more questions there.
Yes, well,
thanks a lot for the talk.
Thank you.
Okay, next up we have our second talk on DOJO. It's the supercompute system scaling for ML training. This talk will be by Bill Chang and Rajiv Kurian from Tesla. Bill is the chief system engineer at Tesla, responsible for design and architecture of high-performance ML training systems. He joined Tesla in 2019, managing system development, and drove the technology behind Tesla's advanced training tile. Prior to Tesla, he worked at Apple, where he managed the Mac transition to Apple Silicon, after managing several generations of Apple Silicon for iOS-based devices. He started his career at IBM Microelectronics, where he held various technical leadership roles in technology development and manufacturing. Rajiv is principal engineer at Tesla, leading system software performance. He joined DOJO in 2020, focused on accelerating end-to-end training workloads on custom large-scale systems. Prior to DOJO, he was responsible for performance optimization and acceleration for autonomous driving workloads at both Waymo and Tesla. Let's go to the talk.
Thank you for the introduction. Before we start, I want to give a shout out to the team. The work we'll talk about today is the work of an incredible team at Tesla. We're here to talk about the system architecture of Tesla's DOJO supercomputer. The goal for DOJO was to build a system from the ground up to accelerate our path to autonomy. The challenge is that this is an area where things are evolving and changing at an incredible pace. There are a wide range of neural network models that are being used for various tasks, such as vision, path planning, and auto-labeling. New model architectures are being introduced all the time, and parameter sizes are increasing exponentially. The data used to train these models are also growing. Video-based training not only expands the size of the training data, but requires more complex 4D labels. And these labeling tasks get more difficult as more ground truth data is needed. Infrastructure also needs to be updated to make up for training for the new models and new training data, and needs to support the increased iteration loops to solve new problems. Today, we'll walk through our approach to building a flexible system architecture and how software can leverage this at scale. For a typical large-scale system, you need to choose the amount of compute, memory, and I/O to optimize for a set of target workloads. You usually do this with servers that package a fixed ratio of compute, memory, and I/O. If you need additional compute, you would add additional servers and get the same fixed ratio, even if it wasn't needed. The difficulty with building an optimized ML training system is that the workloads and requirements are constantly changing. As models get more complex, more compute is needed. Additional memory is needed as parameters are exploding. And training data to feed the models continue to grow, so additional I/O is needed. So knowing the right ratio of compute, memory, and I/O is hard without significantly overbuilding. And even if you found the right balance, when the workloads change, the system needs to be updated. So our approach to this is to build a system that can quickly adapt. And we do this by building flexible, disaggregated components that can be connected together, then provisioned as the workload needs. We start with building an optimized compute block. We need to have a block that can integrate enough compute to elevate the foundation for a large-scale supercomputer. For this, we leverage new technology to give us the compute we need. We use new system-on-wafer technology to integrate 25 D1 dies and 40 I/O dies. We integrate both compute and I/O dies to optimize power efficiency and reach. We utilize heterogeneous RDL to optimize for both high density and high bandwidth, and also provide high power. This integration is different than other large-scale assemblies, as we can maximize performance while achieving high yield. And we do this by using a known good die strategy and leveraging fault-tolerant designs. Each tile starts with fully functional dies that have been tested, binned, and harvested. This allows us to know the performance of the dies before they are assembled and they can be optimally placed. Fully configurable on and off die routing with per lane fault tolerance allows us to yield tiles with some defects with little impact to performance. This new integration enables our DOJO training tile, which is our fundamental unit of scale for compute. This tile integrates 9 petaflops of machine learning compute with 11 gigabytes of high-speed SRAM. Similar to a rack server, this tile includes all the power, cooling, and control needed to run. The key for scaling beyond this tile is the uniform high bandwidth. On tile, this has a 10 terabyte bisection bandwidth, and it has 36 terabytes of off-tile aggregate bandwidth. To scale our compute, all we need to do is connect them together. No additional power or cooling or system design is needed. And similar again to rack servers, they're plug and power on. Next, we need to provide high-speed, high-capacity memory to the training tiles. We have a lot of SRAM on our training tiles, but we need to be able to have DRAM to provide additional capacity to support the large parameter models and to be able to expand as the parameter sets expand. And we do that through the DOJO interface processor. In our first version of our interface processor, we've built a standard card that can be used either in a host or a standalone configuration. This card provides 32 gigabytes of high bandwidth memory at 8 gigabytes of total memory bandwidth. This card interfaces with the training tile using TTP or the Tesla Transport Protocol, which is the same protocol used to communicate die to die and tile to tile. And we can provide 900 gigabytes of TTP bandwidth to enable full memory bandwidth to the tiles. In addition to the custom TTP interface, we have 50 gigabytes of Ethernet bandwidth. Our interface processor provides native hardware support to extend TTP over standard Ethernet. So this means no additional software overhead to bridge between our custom TTP network and standard Ethernet. Lastly, we provide 16 lanes of Gen 4 PCIe interface to the card. In our first iteration, we use the interface processor in a host configuration, and we connect to the host CPU through PCIe. For max bandwidth, we can pair 5 cards together to provide 4.5 terabytes of aggregate bandwidth to the tiles. And that gives us 160 gigabytes of total DRAM per tile edge. And then with 5 cards, we can provide 80 lanes of Gen 4 bandwidth to move data to and from the training tiles. To be able to tie this all together, we need to have a scalable communication network. This network needs to be able to tie together all the components in our system. We need to be able to provide high bandwidth for our compute, provide access to our high-speed memory, and enough I/O to feed training data to the system. We do this through the Tesla Transport Protocol. TTP enables seamless communication across all the levels and layers. Software sees a uniform address space from node to node, die to die, tile to tile, and to the shared memory on the interface processor. The DOJO interface processor provides hardware support to further extend that communication over standard Ethernet. This allows us to add devices onto the standard Ethernet to extend our TTP network. TTP over Ethernet can then allow us to build a Z-plane in addition to our compute plane. This enables shortcuts across our network and provides high-rate-X connectivity using standard Ethernet switches. This allows us to manage latency for sync and control across our 2D compute plane. For example, if we wanted to send data to a die that was over 6 tiles away, it would take over 30 hops. With using TTP over Ethernet, that same data transfer would now only take 4 hops. Moving further out, we've built a DOJO network interface card that enables remote DMA with TTP over Ethernet. This allows us to do DMA to and from any TTP endpoint on our network and leverages switched Ethernet networks to do that. This allows us to bring in remote compute for pre- and post-processing for our workloads. This is an example remote DMA topology where we can connect any number of hosts with our network interface cards to our Ethernet network and allow them to remote DMA with TTP over Ethernet into the shared DRAMs on the interface processors. This allows us to scale out CPU and memory-bound workloads for pre- and post-processing. Putting it all together, this is what our first version of our DOJO training matrix looks like. We connect n by 3 number of training tiles and connect 5 interface cards per tile edge. Those are then connected to host CPUs through PCIe, and then we can extend TTP over Ethernet through standard Ethernet switches to network interface cards on any additional CPU hosts for pre- and post-processing. This matrix then extends out to 3,000 accelerators per exapod, and that gives us over an exaflop of machine learning compute with 1.3 terabytes of SRAM and 13 terabytes of high-speed DRAM. So we've talked through the basic components of the DOJO supercomputer. These components allow us to optimize a system configuration that can accelerate virtually any ML workload. We leverage innovative technologies to build scalable compute blocks, and disaggregation allows us to build a flexible system to adapt quickly to evolving workloads. And each of these components can be updated and upgraded as needed. And we can add additional devices to our high-speed TTP network to expand and add additional functionality. Next, we'll have my colleague Rajiv talk about how software leverages our system at scale.
Thanks, Bill. I'll start off by talking a bit about how software takes advantage of the high bandwidth and flexibility of DOJO to map neural networks onto the system. High TTP bandwidth and support for system-wide fine synchronization primitives lets software treat the entire system as one block. With large amounts of SRAM available in the system, we operate almost entirely out of SRAM, leading to high compute utilization. We also keep a single copy of parameters in the entire system and replicate them just in time, depending on the high TTP bandwidth to hide the replication time. Also, thanks to the high TTP bandwidth, all forms of parallelism can cross die boundaries, whether it be model-based parallelism, data-based parallelism, or tensor parallelism. Let's go through a semi-realistic example to see how models are executed on DOJO. This particular system has 4 tiles in a column and 5 dips each on the north and south edges of the tile column. Parameters start across the dips. Here we show 2 parameters, P0 and P1. Before our training loop starts, parameters typically are sharded across the dips. In our example, P0 and P1 are sharded in the input channel dimension. P0 is placed on the first 2 tiles, and P1 is placed on the last 2 tiles. This is done only once per training run. Like mentioned before, parameters stay sharded in SRAM across training iterations. For every new training iteration, inputs are brought in, sharded across the dips in the batch dimension. Inputs are also distributed across the tiles for processing. In our example, they continue to stay sharded by the batch dimension. A quarter of each input resides on every tile. Before processing the first layer, the shards of parameter P0 are replicated just in time across all tiles. We start by exchanging the shards between the first 2 tiles. Now both tiles 0 and 1 have a full copy of P0. Then we broadcast this replicated parameter P0 to the other tiles. Now every tile has a copy of P0. The first layer is then run in a data parallel manner, and we end up with a quarter of output on each of the tiles. While the compute for this layer is running, we can currently replicate the parameters P1 for the next layer. The next layer will be run in a model parallel manner. So instead of having a full copy of P1 on each tile, we take 2 shards on the last 2 tiles and replicate them on the first 2 tiles. Now there is 1 copy on the first 2 tiles and another copy on the last 2 tiles. So why do we execute in model parallel manner? Well, certain levels provide parallelism mostly in the z dimension, and this can lead to better utilization. For certain other models, the parameters might be so large that they don't fit in a single tile. Model parallel is not out of the norm for DOJO. The DOJO system was built to make model parallelism work. Fine-grained synchronization with small packets allows for moving just the data that you need and do it concurrently with compute. The mapping I'm showing is really a fractal. Systems are composed of tiles, tiles are composed of dies, dies are composed of nodes. So even things that look data parallel at the tile level look model parallel at the die or node level. So the replicated parameters from the previous layer are no longer needed, nor is the input activation from the previous layer. Both are discarded to save SRAM space. Since we plan to run the next layer in model parallel mode, we split the previously computed input activations for the layer in the channel dimension such that half of it remains on the tile of origin and the other half moves to another tile. Now each tile computes the partial output for this n/4 batch in parallel. Why is it partial? Because only half the input channels existed on each tile. The partial outputs now need to be reduced to produce the final output for this n/4 batch. The partial sum computation is pipelined with the rest of the layer, and again our small packet size, fine-grained synchronization primitives, and low latency network makes pipelining such workloads easy. The same computation runs for every other n/4 batch, thus producing the outputs sharded by batch again. This was an example of layers are executed with a combination of model and data parallelism. We just talked about how the high TTP bandwidth leads to programs that exploit all kinds of parallelism to accelerate model training. However, compute is only part of the bottleneck. Data loading and post-processing can become bottlenecks and lead to ML compute underutilization. Video-based training workloads dominate at Tesla. For such workloads, data loading requires flexibility, and while our programmable hardware can be used to offload some of it, we want to maintain the option of using host compute to maintain flexibility for researchers. Training on random video samples can lead to an explosion of video decode requirements. Thus, even at this tier, we need a combination of flexibility and high throughput to match the ML compute. Here we show the data loading requirements of 2 internal models broken down into a few host resource categories. Each can be comfortably served by a single host while keeping the ML compute well utilized. However, for the same amount of ML compute, the data loading resources required by this third model would far exceed the capacity of one host. This is a common pattern that we see. While some networks are compute bound, others can be data loader bound. If you have a fixed ratio of ML compute to host compute, we either risk under-provisioning host compute or over-provisioning it. In the spirit of the rest of the system, our host layer is also built to be disaggregated. Each host in this tier is provisioned with a DNIC card that Bill talked about, and this allows it to speak TTP over Ethernet and DMA directly into the DIPs. The commodity Ethernet switch setup allows us to use a flexible number of hosts tailored to meet the needs of a particular model. Here we see a logical diagram of how 4 machines could cooperate to shard the input batch across multiple DIPs. This setup allows I/O, memory, and ML compute to form disaggregated resource tiers. Each model can be provisioned with the ideal mix of resources that it needs, maximizing utilization. Here we see how Model 3 ends up using more I/O and host resource compute than the other models. So, to conclude, we started with high-performance ML compute and memory tiers and connected them with high bandwidth. This high bandwidth and the inherent programmability of the hardware allows for full exploitation of parallelism by the software. Finally, vertical integration of even the I/O and host compute tier leads to a system composed of disaggregated resources that can be combined for optimal utilization and performance. This lets us build a system not only suitable for models of today, but also hopefully for models that we're yet to see. Thank you.
Okay, thank you, Bill and Rajiv. We'll go to questions now. I'm going to combine 2 questions on programming systems. So Ramesh Narayan Swamy from Synopsys asks, what is the programming language or framework? And then Asmita Nishur from Intel asked, is model and data parallelism per layer determined and mapped by the compiler?
So we don't support any programming languages like C++. Our target is PyTorch. So we take a PyTorch network, we have our own internal IR, we translated it to our internal IR and compile it from there. And in terms of whether the compiler does model parallelism and data parallelism at a per layer, yeah, approximately something like that. Like I would say the compiler has full visibility of the graph, and whether it decides to do data parallelism, model parallelism, recompute, spill, fill, is all decided by the compiler.
Thanks. Ashutosh Dar from NVIDIA asks, what is the intended use case for DOJO? Only vision networks like CNNs for self-driving, or are LLMs, GNNs, etc. part of the target as well?
All networks like LLMs and GNNs are definitely part of the target. In fact, the models that we use in cars are chock full of transformers, RNNs, CNNs, of course, and the flexibility that we put into the hardware was specifically built so that we could support multiple kinds of models.
Right. Cliff Young from Google asks, his question is, it seems your system architecture scales up compute and SRAM quadratically, but it scales up HBM and off-system I/O only linearly along the perimeter. How has this scaling affected your use of the system and your goals for flexibility? Can you say how many tiles you typically plan to deploy?
I'll answer part of this, and then Rajiv can answer the second part. So I'll start by, in terms of number of deployment on the tiles, we have 120 tiles per Exapod. And so our plan is to continue to build Exapod, so each time it'll be 120 tiles. To the question of the fixed ratio, the ratio scaling for DRAM, this is a choice in terms of how we've built the configuration. They are disaggregated components. So we actually have built systems with different ratios, but we've chose this configuration since this seems to fit best with the workloads that we need to run, and it scales well for that.
Yeah, in terms of DRAM and I/O bandwidth, I think we consider the tile as a big unit with 11 gigabytes of SRAM. So large matrix multiplications can be blocked effectively on that 11 gigabytes of SRAM. So the DRAM needs are lower. Of course, we still need them when you have a large number of parameters in the model. So for large language models, we would probably have configurations that look a little different and just have a lot more DRAM surrounding a tile.
Maybe a bit of a follow-up question related to that. Adam Butts at D. Shaw Research asked, what trade-offs led to the choice of one fixed dimension of 3 DOJOs in the scale-up system? I assume it was partly to limit inter-pod communication to one edge or dimension, but why 3 versus 4 or some other number?
There is some physical limitations to that, but overall this went into looking at different configurations that made the most sense. For example, we actually have two planes in each Exapod, but the choice was to make a 2x3 per pod for it met all the performance and workload requirements.
Okay, there's interest, of course, in performance. Anastasi from Intech asked if you can share performance measurements. I'm not sure if you will be able to or not, but also Ashutosh Dar from NVIDIA asked what kind of math utilization you might typically get from a full wafer.
For performance numbers, we have internal numbers that we're not ready to share yet. I think we'll share them during Tesla's AI Day 2, which is on the 30th of September. We're pretty happy with the internal performance, and I think we're going to focus on our internal models for a while. For math utilization for large matrix multiplications, we see above 90% utilization at the die and tile level. And for larger networks, I think, again, we're going to share utilization numbers in the future.
Andre Jacques from the University of Sherbrooke asks, what protocol do you use on top of Ethernet? Is it based on TCP/IP or UDP, or is it custom?
It's a custom protocol.
And then another question on the Ethernet. Can you give a sense, James Tringali asks, can you give a sense of the relative latency cost of sending TTP between tiles versus over the Z-axis Ethernet links?
All I'll say is it is higher latency than staying on the compute network, but it is lower latency than, let's say, off-the-shelf protocols.
I think another thing I would add is the compiler is well aware of the latencies, and it chooses the right physical layer based on the communication pattern that we need.
Thank you. Yeah, again, we have a lot of interest in the Q&A on Slack if you're able to get to answer some more questions. But for now, thanks a lot for the talk.
Thank you. Thanks.
Okay, now we'll go into our final talk in the session. The talk is on the Cerebras architecture deep dive, a first look inside the hardware-software co-design for deep learning. The speaker is Sean Lai. Sean is a computer architect who has worked on a variety of technologies, including transactional memory, high-performance CPUs, networking, storage, and distributed systems. He was a lead architect and fellow at AMD. Now he is the co-founder and chief hardware architect at Cerebras, where he's building the hardware and software for their ML accelerator solution. Let's go to Sean's talk.
Hi everyone, I'm Sean, co-founder and chief hardware architect at Cerebras Systems. We started Cerebras with a vision to drastically change the landscape of compute for AI. And today, I will share with you a deep dive into our hardware-software co-designed architecture to meet the demands of ML in the future. For those of you who don't know about us, Cerebras began in 2016, and our mission is to solve the problem of AI compute by building a full AI accelerator solution, from chip to system to software. We now have over 400 engineers with offices around the world. And this August, we were inducted into the Computer History Museum here in Silicon Valley. That was a really proud moment for all of us at Cerebras. And we now have customers using our systems across the spectrum, from large enterprise to HPC and to government. What an incredible journey the last few years have been for all of us here at Cerebras and for the entire ML industry. But we're here today because we're really just at the beginning of what neural networks can do, and we're already reaching a pace where traditional approaches just can't keep up. In 2018, state-of-the-art neural networks had 100 million parameters, and that was a lot. And you fast forward 2 years later, and we got the famous GPT-3 with 175 billion parameters. And there's no end in sight. Tomorrow, we will want to run models with trillions of parameters. Now that's over 1,000 times more compute in just 2 years. Over 3 orders of magnitude more compute in just 2 years. And this is the grand ML demand challenge in front of us all. At Cerebras, we believe that we can meet this unprecedented demand. We can't do it by relying on just a single solution. It has to be addressed by making substantial improvements, order of magnitude or more, across a broad spectrum of multiple different components to meet this unprecedented demand. We need order of magnitude improvements in the core architecture performance, so we can go beyond just brute force flops. We need order of magnitude improvements scaling up. Moore's law simply isn't enough. We need order of magnitude improvements in scaling out to improve and simplify clustering substantially. All of that is required for us to have any hope of keeping up with this ML demand. Is that even possible? It is, but only with an architecture that's co-designed from the ground up, especially for neural networks. And in this talk, I'm going to take a deep dive into the Cerebras architecture to show you how we do this. First, at the heart of all computer architecture is the compute core. And at Cerebras, we set out to architect a core that's specially designed for the fine-grained, dynamic sparsity in neural networks. So this is a small core design, quite literally. This is our core. It's only 38,000 square microns in size, and half of that silicon is used 48 kilobytes of SRAM memory. And the other half is logic, made up of 110,000 standard cells. The entire core runs at an efficient 1.1 gigahertz clock frequency and consumes only 30 milliwatts of peak power. Next, let's take a closer look. First, at the memory. Traditional memory architectures, such as GPUs, use shared central DRAM. But DRAM is both slow and far away when you compare that to the compute performance. Even with advanced bleeding-edge techniques like interposers and HBM, the relative bandwidth for memory is significantly lower than the core data path bandwidth. For example, it's very common for compute data paths to have 100 times more bandwidth than the memory bandwidth. This means each operand from main memory has to be used at least 100 times in the data path to keep utilization high. And the traditional way to handle this is by using data reuse through local caching or local registers. But there actually is a way to get full memory bandwidth to the data paths at full performance. And that's by fully distributing that memory right next to where it's being used. This enables memory bandwidth that's equal to the operand bandwidth of the core data path. And the reason this is possible is, quite frankly, just physics. Driving bits tens of microns from local memory to data path, all on silicon, is much easier than through a package to an external device. So next, let's look at how this memory is designed. Each small core has 48 kilobytes of local SRAM dedicated to the core. And that memory is designed to have the highest density while still providing full performance. And this density and performance is achieved by organizing the memory into 8 single-ported banks that are 32-bit wide each. With that degree of banking, we actually have more raw memory bandwidth than the data path actually needs. So we can maintain full data path performance directly out of memory. That's 2 full 64-bit reads and 1 full 64-bit write per cycle. It's important to note that all of this memory is independently addressed per core. There's no shared memory in the traditional sense. To enable truly scalable memory, all the sharing between cores is done explicitly through the fabric. In addition to the high-performance SRAM, we also have a small 256-byte software-managed cache, and that's used for frequently accessed data structures such as accumulators. This cache is designed to be physically very compact and close to the data paths so that we can get ultra-low power for these frequent accesses. With this distributed memory architecture, we're able to achieve a mind-boggling level of memory bandwidth. If you normalize to the GPU area, that's 200 times more memory bandwidth within the same GPU area directly to the data paths. Now, with that level of memory bandwidth, we can do some really remarkable things. We can run matrix operations out of memory at full performance across all blast levels. Traditional GPU architectures with limited off-chip memory bandwidth, they're limited to running only gems at full performance. That's matrix-matrix multiplies only. In fact, you can see that any blast level below full matrix-matrix multiply requires a massive jump in memory bandwidth. That's not possible with traditional architectures. But with enough memory bandwidth, you can enable full performance all the way down to AXB, which is a vector scalar multiply. And within neural network computation, this is really important because it enables fully unstructured sparsity acceleration. And that's because a sparse gem is just a collection of AXB operations, one operation for every non-zero element. This level of memory bandwidth is a prerequisite for unstructured sparsity acceleration. But additionally, we need a compute core that can accelerate that sparsity. And the foundation of the Cerebras core is a fully programmable processor that can be made to adapt to the changing field of deep learning. Like any general purpose processor, it supports a full set of general purpose instructions. That includes arithmetic, logical, load, store, compare, and branch instructions. These instructions are fully local to each core, stored in the same 48 kilobytes of local memory as the data. And this is important because it means every one of these small cores is independent. And that enables very fine-grained dynamic computation globally across the entire chip. These general-purpose instructions, they operate on 16 general-purpose registers, or GPRs, and they run in a compact 6-stage pipeline. On top of this general-purpose foundation, we have hardware support for tensor instructions that are intended for all data processing. These tensor ops execute on the underlying 64-bit data path, which is made up of 4 FP16 FMAC units. To optimize for performance and flexibility, our ISA has tensors as first-class operands, just like general-purpose registers or memory. And here's an example of an FMAC instruction that's operating on 3D and 2D tensors as operands directly. And we do this by using data structure registers, or DSRs, as operands to the instructions. And our core has 44 of these DSRs, each of which contains a descriptor with a pointer to the tensor, and other key information, such as length, shape, and size of that tensor. With these DSRs, the hardware architecture is flexible enough to natively support up to 4D tensors that could be in memory, or fabric streaming tensors, or FIFOs and circular buffers. Now, behind the scenes, there are hardware state machines that use the DSRs, and they sequence through the full tensor at full performance on the data path. On top of these tensor ops, the core uses fine-grained data flow scheduling. Here, all the computation is triggered by the data. The fabric transports both data and associated control directly in the hardware. And once the cores receive that data, the hardware triggers a lookup of instructions to run. And that lookup is entirely based on what's received on the fabric. With this data flow mechanism in the cores, the entire compute fabric is a data flow engine. and it enables native sparsity acceleration because it only performs work on non-zero data. We filter out all the zero data at the sender, so the receiver doesn't even see it. Only non-zero data is sent, and that's what triggers all the computation. So not only do we save power by not performing the wasted compute, but we get acceleration by skipping it and moving on to the next useful compute. Since the operations are triggered by single data elements, this supports ultra-fine-grained, fully unstructured sparsity without any performance loss. To complement the dynamic nature of data flow, the core also supports 8 simultaneous tensor operations. That's what we call microthreads. These are independent tensor contexts that the hardware can switch between on a cycle-by-cycle basis. The scheduler is continuously monitoring the inputs and the output availability for all the tensors that are being processed and has priority mechanisms to ensure that critical work is prioritized. Microthreading drives up utilization when there's a lot of dynamic behavior by switching to other tasks when there would otherwise be bubbles in the pipeline. With this fine-grained, dynamic, small core architecture, we can achieve unprecedented compute performance, as high as 10 times higher utilization than GPUs on unstructured sparse compute, or potentially even more with higher sparsity. So now, coming back to the grand challenge in front of us, this is how we can get an order of magnitude level improvement from the core architecture. So next, let's look at how we scale that up. Traditionally, scaling up within a chip has been the domain of the fabs. Moore's law has carried our industry for decades, enabling denser and denser chips. And today, Moore's law is still actually alive and well, but it's only giving relatively incremental gains, maybe a 2 times improvement per process generation. And that's simply not enough. So we asked ourselves, can we amplify Moore's law and get an order of magnitude or more improvement? And the traditional way to amplify Moore's law is to make larger chips. So we did that. And we took it to the extreme. This is the Wafer Scale Engine 2, the WSC2. It's currently generally available and being used by our customers every day. It's the largest chip ever built, at 56 times larger than the largest GPU today. At over 46,000 square millimeters in size, with 2.6 trillion transistors on a single chip, we can fit 850,000 cores. With all of those cores integrated on a single piece of silicon, we get some truly mind-boggling numbers for memory and fabric performance, because everything is on chip. And we built a specially designed system around it, called the Cerebras CS2. This was co-designed around the WSC2, enabling the wafer scale chip to be used in a standard data center environment. It's truly cluster-level compute in a single box. And here's how we build up to that massive wafer from all of those small cores. First, we create a traditional die with 10,000 cores each. But instead of cutting up those die to make traditional chips, we keep them intact, but we carve out the largest square within the round 300 millimeter wafer. And that's a total of 84 die with 850,000 cores, all on a single chip. But all of this is only possible if the underlying architecture can scale to that extreme size. And the fundamental enabler is the fabric. It needs to enable efficient and high-performance communication across the entire wafer. And our fabric does this by using a 2D mesh topology that is well-suited to scale on silicon with extremely low overheads. This fabric ties together all the cores, where each core has a fabric router, and the fabric router has 5 ports with 32-bit bidirectional interfaces in each of the 4 cardinal directions, and 1 port facing the core itself. This small port count enables only a single clock cycle latency between nodes, and it enables low-cost, lossless flow control with very low buffering. The fundamental data packet is just a single FP16 data element optimized for neural networks. And along with that FP16 data, there is 16 bits of control information making up a 32-bit ultra-fine-grained packet. To optimize the fabric further, it uses entirely static routing, which is extremely efficient and low overhead while perfectly exploiting the static connections of neural networks. to enable multiple routes on the same physical link, we have 24 independent static routes that can be configured. We call those colors. All of them are non-blocking between one another, and they're all time multiplexed onto the same physical links. And lastly, neural network communication inherently has a high degree of fan-out, so our fabric is designed with native broadcast and multicast capabilities within each router. Now that we have a scalable foundation, we need to scale it. And scaling within a single die is simple. And scaling beyond the die, what we do is we extend the fabric across those die boundaries. We cross less than a millimeter of scribe line, and we do this using high metal layers within the TSMC process. And this extends that 2D mesh fabric compute fabric to a fully homogeneous array of cores across the entire wafer. The die-to-die interface is a highly efficient source synchronous parallel interface. But at this wafer scale, this adds up to over 1 million wires, so we have to have redundancy built directly into the underlying protocol. And we do that with training and auto-correction state machines. With these interfaces, even with defects in the fab process, we get a fully uniform fabric across the entire wafer. Now these seemingly simple short wires, they're a big deal because they span less than a millimeter of distance on silicon. When you compare that to traditional SerDes approaches, the difference is massive. And it's just like the memory, it's just physics. Driving bits less than a millimeter on chip is much easier than through a package, connectors, PCBs, and sometimes even cables. And this results in orders of magnitude improvement compared to traditional I/O, as you can see from the table. We're able to achieve about an order of magnitude more bandwidth per unit area and almost 2 orders of magnitude better power efficiency per bit. And all of this translates into unprecedented fabric performance across the entire wafer. If you normalize to GPU equivalent area, that's 7 times more bandwidth than GPU die-to-die bandwidth in the same GPU area at only 5 watts of power. At this level of global fabric performance, that's what enables the full wafer to operate as a single chip. And that's important because with such a powerful single chip, we can solve some really large problems. It enables us to run extremely large neural networks all on a single chip. The WSC has more than enough performance and capacity to run even the largest models without partitioning or complex distribution. Now this is done by disaggregating the neural network model memory weights and the compute. We store all of the model weights externally in a device called MemoryX, and we stream all of those weights onto the CS2 system as they're needed to compute each layer of the network, 1 layer at a time. The weights are never stored on the CS2, not even temporarily. As the weights stream through, the CS2 performs the computation using the underlying data flow mechanisms in the core. Each individual weight triggers the computation as an individual AXP operation. Once each weight is complete, it's discarded, and the hardware moves on to the next element. Now, since the weights are never stored on the chip, the size of the model is not constrained by the memory capacity on chip. On the backward pass, the gradients are streamed out in the reverse direction back to the MemoryX unit where the weight updates happen. So let's take a deeper dive into how the computation is actually performed so we can see how the architecture properties uniquely enable this capability. Neural network layers boil down to matrix multiplication. And because of the scale of the CS2, we're able to use all 850,000 cores of the wafer as a single giant matrix multiply array. And here's how that works. For transform models like GPT, activation tensors have 3 logical dimensions: batch, sequence, and the hidden dimension. We split these tensor dimensions over the 2D grid of cores on the wafer, as you can see in the picture. With activation stored on the core, where the work is actually being done, the next step is to trigger the computation on those activations. This is done by using the on-chip broadcast fabric. That's what we use to send the weights and the data and commands to each column of cores. Using the hardware data flow mechanisms, the weights then trigger the FMAC operations directly. These are the AXP operations. We start by broadcasting the row of weights across the wafer. Each element of the row is our scalar. Within that row, there are multiple weights that map onto a single column of cores. So when there's sparsity, only those non-zero weights are broadcasted to the column of cores, triggering those fmac computations. We skip all of the zero weights, and we stream in the next non-zero weight, and this is what produces a sparsity acceleration. The weight value is multiplied by each of the activations and added into a local accumulator, which resides in the software-managed cache. The fmac compute is performed using a tensor instruction with the activations as a tensor operand. Once all the weights for the row have been received, each core contains a partial sum that needs to be reduced across the row of cores. And that reduction is then triggered by a command packet broadcast to all the cores of each column. Again, using the data flow scheduling mechanisms, once the core receives the command packet, it triggers the partial sum reduction. The actual reduction compute itself is done using the core's tensor instruction, this time using a fabric tensor as operand. Once it receives the commands, the core communicates using a ring pattern on the fabric, which is set up using the fabric static routing colors. And using microthreads, all of this is done in parallel with the fmac compute for the next weight row, which started at the beginning of the partial sums. Once all the rows in the weights are complete, the full gem operation is done, and all the activations are in place for the next layer. All of this enables neural networks of all sizes to run with high performance, all on a single chip. That's made possible by the unique core, memory, and fabric architecture. This means extremely large matrices are supported without blocking or partitioning. Even the largest models with up to 100,000 by 100,000 map-mul layers can run without splitting up the matrix. When you bring this together across the single WSC2 chip, this results in 75 petaflops of FP16 sparse performance, or potentially even more with higher sparsity, or 7.5 petaflops of FP16 dense performance, all on a single chip. Now bringing this back to the grand ML challenge in front of us, this is how to achieve an order of magnitude level improvement in scaling up. Now let's talk about the last component, cluster scale out. Clustering solutions already exist today. So why is it still so hard to scale? Let's look at existing scale-out techniques. The most common is data parallel. This is the simplest approach, but it doesn't work well for large models because the entire model needs to fit in each device. To solve that, the common approach is to run model parallel. This splits the model and runs different layers on different devices as a pipeline, but as you can see, as the pipeline grows, the activation memory increases quadratically to keep the pipeline full. To avoid that, it's also common to run another form of model parallel by splitting layers across devices. But this has significant communication overhead, and splitting individual layers is extremely complicated. Because of all of these constraints, there is no single one-size-fits-all way to scale out today. In fact, in most cases, training massive models requires a hybrid approach with both data parallel and model parallel. So although scale-out solutions technically exist, they have many limitations. And the fundamental reason is simple. In traditional scale-out, memory and compute are tied to each other. Trying to run a single model on thousands of devices turns the scaling of both memory and compute into distributed constraint problems that are interdependent. And here's the result of that complexity. This graph shows the largest models trained on GPUs over the last few years and the different types of parallelism used. As you can see, as the models get larger, the more types of parallelism is needed. And this results in a tremendous amount of complexity. For example, you can see that the level of tensor model parallel is always limited to 8, because that happens to be the number of GPUs that are typically in a single server. And as a result, the majority of parallelism in these very large models is actually pipeline model parallelism. But that's actually the most complicated because of the memory trade-offs. So training these large models on GPU clusters today requires navigating all of these bespoke distributed system problems. And this complexity results in longer development times and often suboptimal scaling. On the other hand, Because the Cerebras architecture enables running all of these models on a single device without partitioning, scaling becomes easy and natural. We can scale with only data parallel replication. There's no need for any complicated model parallel partitioning. We do this with a specially designed interconnect for data parallel. This is called SORMX. It sits between the MemoryX units that hold the weights and the CS2 compute systems, but it's independent from both of them. SORMX broadcasts weights to all CS2s, and it reduces gradients from all CS2s. Internally, SORMX uses a tree topology to enable modular and low overhead scaling. And because it's modular and it's disaggregated, we can scale to any number of CS2s with exactly the same execution model as a single system. Scaling to more compute is as simple as adding more nodes to the SORMX topology and adding more CS2 systems. And that is how we address the last component of the grand ML demand challenge, to drastically improve and simplify scale-out by an order of magnitude or more. So now let's go back to where we started today. In the past couple of years, we have seen over 3 orders of magnitude greater demand from ML workloads. And there's no sign of slowing down. In the next couple of years, this is where we'll be. We asked ourselves, is this even possible? At Cerebras, we know it is. But not by using traditional techniques, only by improving the core architecture by an order of magnitude with unstructured sparsity acceleration, only by scaling up by an order of magnitude with wafer scale chips, and only by improving cluster scale out by an order of magnitude with truly scalable clustering. With all of these, that future is achievable. Neural network models are continuing to grow exponentially. Few companies today have access to them, and that list is only getting smaller. With the Cerebras architecture, by enabling the largest models to run on a single device, data parallel only scale out, and native unstructured sparsity acceleration, we're making these large models available to everyone. Thank you very much.
Okay, thank you, Sean. Let's go to the questions. First one, Ashutosh Dar at NVIDIA asks, scaling across thousands of compute PEs in a wafer seems like a very complicated scheduling and placement problem. How are you tackling this challenge? How much performance gain have you been able to achieve by improving the compiler and scheduler on common deep learning workloads?
That's a great question. I think the way we think about it is kind of in 2 parts. Coordinating across 850,000 cores is clearly quite complicated. And so we don't have any central coordination at all. All of the synchronization, all of the coordination between the cores is all done in a distributed fashion by the code that's running on the cores. And so that's what's actually running on the wafer. And then in terms of how do we actually think about what each core should be running, we have an overall compiler that maps out each individual layer across all of those cores and very much exploit the uniform nature of the overall layer types and computation, like in the MapMo example that I gave. And so that greatly simplifies a lot of the overall mapping in the compiler.
Right. Thanks. Jeff Smith from Citadel Securities has a number of questions on fabric routing. He asks, are routing colors different from typical NOC virtual channels? Where are the available static routing algorithms? Or where, yes, and also dimensional ordering. What approaches are used to route around defective grid locations?
What we call colors is similar to traditional virtual channels, but we don't think of them as virtual channels for one primary reason, is that typically a virtual channel is has resources for the entire link of the actual storage, whereas here we have resources for the entire route only. And so that's why we think of these as kind of virtual routes, so to speak. That saves significantly the amount of buffering resources we need. So instead of having buffers per link, we have buffers per route. The second question was, can you remind me the second question, Ron?
Where are the available static routing algorithms and or dimensional ordering?
Yeah, so all of the routing algorithms are done upfront as a configuration into some very basic routing tables. There is no traditional routing kind of smarts in the router itself. There is no traditional dimensional order routing, any of that. All of the deadlock avoidance needs to be planned upfront by the software that programs the static routes into each of the routers. Again, this is done so that we can keep the router logic to the bare minimum and keep it as simple as possible.
Mm-hmm. Then Jeff Smith from Citadel had one other question. Why not scavenge another dozen complete dies around the currently unused or the currently used rectangular region?
Yeah, that's a great question. Primarily to keep the physical packaging simpler. You'd be amazed how much simplicity you get from a square versus a, whatever multi-sided shape you would get out carving out something that looked like more like the wafer. Right. And so it's primarily a physical constraint.
Jay Lee also is asking about, can you elaborate on how on TSMC allowing the topside metal to run across the scribe line?
Yeah, so this process was developed in tight collaboration with TSMC. Clearly, this is not a standard process that they offer off the shelf. And so it required a lot of very, very close collaboration in terms of how TSMC uses the scribe lines. And in particular, they typically use the scribe line area for things like test structures that are used by the fab, by TSMC. And so we had to negotiate and work with them very closely to make sure that we can, cross those scribe lines and still, maintain the level of testability and manufacturability that they have at the fab.
Right. And then there's a number of questions about memory X. Let me list a few of them and give you a chance to address them. Xiaoyu Ma from Google asks, because the model is stored in the off-wafer memory X, how often are you bottlenecked by moving the data between the compute wafer and the memory X? Ashutosh Dar from NVIDIA asks what the bandwidth is between the memory X and the CS2 wafer, what kind of topologies are supported. And then Jeff Smith from Citadel asked if you could elaborate at all on the memory X structure and interface to the WSE proper.
Yeah, so the WSE has I/O out of the wafer along the edges, and you can almost think of them as kind of an extension of the on-wafer fabric. And the CS2 system basically brings that I/O out onto a standard-based Ethernet-like interface. And we have 1.2 terabits per second of I/O bandwidth, which is what we use to stream the weights in from the memory X. That's not a bottleneck in most cases, primarily because of the size of the models. And so ultimately, there's a balancing between the amount of I/O that you have versus the amount of compute that you need to perform. And so for all the state-of-the-art models, and as models get larger, in fact, it helps. There's plenty of I/O for that. In terms of the memory X topology, the actual networking level topology is really the tree topology that I showed through that SORMX interconnect. So we support a multi-layer broadcast and reduced tree to connect from the single memory X unit to the multiple WSC wafers and CS2 systems.
Great. Thanks a lot. Thanks for the great talk. We'll take the rest of the Q&A to Slack.
Thank you, Ronnie.